On October 29, 2018, Lion Air Flight 610 took off from Jakarta. In the flight report, which shows the plane's altitude over time, you can see that the plane was in full thrust during takeoff. But at a certain point, the nose of the plane kept lurching downward. The pilots couldn't figure out why this was happening. The captain asked the first officer to check the quick reference handbook. They couldn't find the solution. The pilots continued to fight with the MCAS. The plane struggled to gain altitude. Reports show it was likely because the computer was getting incorrect sensor data, pushing the plane toward the earth below. 12 minutes after takeoff, the plane crashed into the Java Sea.
Just a few months later, another flight crashed in Indonesia and killed 189 people. These two flights were operating the same plane, the Boeing 737 MAX 8. This was an upgraded version of its predecessor Boeing 737 with a much bigger engine. In order to work around the increased power because of the bigger engine, Boeing installed a new software, so-called Maneuvering Characteristics Augmentation System, or the MCAS. The software automatically pushed the nose downward if the pilot flew the plane too high of an angle. For now, after the tragic accidents, nearly every 737 MAX 8 in service has been grounded. My name is Mohammed Holloway, and today we are going to talk about software certification with a focus on the avionics industry. In avionics, the criticality of a system is based on the consequences of its failure and the risk of this failure leading to loss of equipment or human lives. When an aircraft is deemed safety critical, an authority such as the European Aviation Safety Agency for civilian aircraft or the DGA for French military and government state aircraft generally requires that the methodology used for the system development process has been proven and recognized as acceptable. This authority carries out one or more audits to ensure that the industrial development process complies with the objectives specified in the standards, following a certification process. A certification process is essential in regulated safety critical fields. In avionics, it's mandatory. Its effectiveness has been demonstrated by a constant reduction of fatal accidents through the years despite the growth in air traffic. The several independent assessments are of utmost importance to ensure to the system environment and its future users that the level of trust is in line with the intended use. So how can we ensure the safety of a software? Safety uses systems theory and systems engineering to prevent foreseeable accidents and minimize the consequences of unforeseeable accidents. It takes into account the loss of human lives or injuries, the destruction of assets, mission failures, and environmental damages. Safety standards are guidelines edited by regulation authorities to determine if the product will perform reliably in its operational context. There are many systematic strategies to determine and quantify modes, effects, and impacts of failures. The most common conventional strategies to ensure safety are failure mode effects and analysis, FMEA, and fault-free analysis, the FDA. These two strategies are fundamentally different. The fault-free analysis is a top-down system evaluation procedure in which a qualitative model for a particular undesired event is formed and evaluated. Like in this example, first we define the top event of the system. For instance, our server is down for more than 4 hours. Then we define the tree-top structure where the events and the conditions that lead to the top event are. After that, keep repeating this process at different successive levels unless the fault tree is completed. To solve the fault tree, we examine all the events and conditions and find dependencies among itself. At the end, we use statistical data to evaluate, predict, and improve the future performance of the system. On the other hand, the FMEA is a reliability evaluation design technique. It examines potential failure modes within a system and its equipment to determine the effect on equipment and system performance. Each failure mode is classified according to its impact on mission success and personnel or equipment safety. We will see an example using the Reliance FMEA worksheet. Our function will be hot water is dripped over the coffee grounds. Now we can define a failure for the function. The arm is not positioned over the coffee grounds. At this point, you can see where we are heading. We're not getting our coffee, but let's formalize this with FMEA effects. We could list many effects. For instance, coffee is not prepared. Next, we have to assign a severity to this effect. Severity is one of the components used to assess the risk levels of our FMEA items. So depending on your caffeine addiction, you may think this is a severity of 10 because you cannot imagine your morning without a coffee. For now, we will assign our effective severity level of 8, which indicates that this effect involves a loss in the primary function of the coffee maker. Now we have to analyze our potential causes. We will go for user do not move his arm over the coffee grounds before turning on the coffee maker. Next, there are two critical values we have to populate, occurrence and detection. For occurrence, we will assign a value of 5 because this happens occasionally. For detection, we will assign a value of 10 because we do not have any method to detect this cause when it occurs. Once detection is entered, Reliance FMEA software will automatically calculate the RPN or the risk priority number. We can see that it's 400 and a high risk item noted by the red color. So how can we implement the safety strategies to certify our software? In the avionics industry, systems and components, whether separately or interconnected, must be designed so that the occurrence of catastrophic failures that reduce flight or landing safety is extremely improbable and is not due to a single failure. This is known as a FailSafe design concept. Audits are a way of verifying the technical content produced by the processes implemented. During this type of exercises, applicants who are the certification candidates need to demonstrate their ability to design software, overcome problems, and size the resources in order to meet all regulatory objectives. These objectives are determined by the software's criticality level, which is based on a system analysis that identifies how the software may contribute to failure condition scenarios. In this table, you can see conditions according to the severity of their consequences, on a scale from 1 to 5, with 1 being no safety effect and 5 being catastrophic. For instance, if the failure condition causes fatalities or incapacities to the crew or the passengers, or causes hull loss to the aircraft, it is considered catastrophic. But how many times could each failure happen? Well, if the failure condition is considered catastrophic, then its acceptable quantitative probability of occurring should be less than 10 to the power of minus 9 per flight hour, and its acceptable qualitative probability should be extremely improbable. At the aircraft level, which should be capable of withstanding 100 catastrophic failure conditions, and for which 10% of crashes are due to technical failures, it is deemed economically and socially acceptable to lose one plane for every 1 million flight hours. So in order to avoid crashes, we seek to reduce the risk of introducing errors during the development phase. Now let's have a brief look to a standard software development model, which is the VModel. Its life cycle consists of typical stages in the software development. User requirements are transformed into software requirements, which are then used as a guide to draw up software architecture, before moving to detailed design and coding. This is followed by tests for each function conducted by unit, followed by integration tests, software tests, and acceptance tests by the customer. Each test plan is prepared in the downward part of the V cycle. So in order to reduce the criticality level of the software engineering process, we can define constraints or objectives in the model to be complied with. And such objectives, for instance, could be found in the key standard among the guidelines used in avionics, which is the DO178C. The DO178C is a key standard among the guidelines used in avionics. It sets out the safety conditions applicable to safety-critical avionics software in commercial and general avionics, and it's based on 4 principles. The first one, software is so complex that it is practically impossible to guarantee that it is error-free. The second one, even if the development process is reliable, errors can happen. The third one, the DO178C, is a document that defines objectives to fulfill. The fourth and the last one is quality assurance of the software development should ensure that the safety measures were correctly implemented. Safety analysis assign a safety criticality level to each software solution, which reflects the severity of failure conditions that they contribute to. This safety criticality level is called the Development Assurance Level, the DAL, and ranges from A to E. The closer this level to A, the higher the number of DO178C objectives will be. If the failure conditions is considered to be catastrophic, then the development assurance level of the contributing software will be classified as a DAL-A, and the DO178C will require it to satisfy 71 objectives. These 71 objectives do not impose any lifecycle requirements, but define separate processes which could be combined to describe the lifecycle of a given project. There are 3 types of processes, and each process has its own objectives to fulfill. The first type of process is the planning process that includes objectives such as the software's function must be systematically specified in a general specifications document based on the system requirements. The second type of processes is the development process that includes objectives such as the source code should be developed in compliance with the coding standards. The third and last type of processes are the integral processes that include objectives such as traceability should be established between data items. This leads us to the software verification process, which is the most important chapter in the DO178C. In terms of volume, it includes 13 pages of description compared to an average of 5 in other chapters. And in terms of the resulting workload, for instance, for the Airbus 380, there are 4 lines of tests for every line of embedded code. Moreover, in verification, the importance of independence is highlighted. It requires tasks to be clearly distributed to ensure that the activities or appraisals were correctly conducted by independent third party. At least 3 people are needed in a team in order to develop a DAL-A level software. According to verification independence requirements, we need a developer and/or reviewer of data produced by the auditor, an auditor and/or a reviewer of a data produced by the developer, and a quality assurance manager. Another crucial keyword in verification is terminology. For example, if you are looking to verify your software with a standard DO178C, you can ignore the difference between validation and verification activities. Both are named verification. But the DO254 standard is clear on this matter. It refers to validation as the activity that involves ensuring the requirement under consideration is compliant with and supports upper-level requirement. For example, are we building the right product? As for verification, this entails making sure the result obtained when executing the implementation meets expectations. For example, are we correctly building the product? Until now, the whole certification process sounds good, but at the end, what are the challenges? In the avionics industry, whereas the effectiveness of guidelines is recognized, according to the data from Avionics Safety Network, there has been a continuous drop in the number of air accidents as it appears in this data. In practice, implementing certification guidelines is seen by manufacturers to be costly and time-consuming exercise, requiring actions that are considered to be superfluous in the prototyping phase. Thus, standard guidelines are not always implemented. For example, in the military field, manufacturers rarely apply rigorous auditable processes when developing safety-critical software. An argument often heard is that the system is made for war, so safety issues are secondary. We are also seeing new players enter the fields of drones and autonomous cars, implementing innovative industrial techniques and technologies such as agile methods, artificial intelligence, and model-based safety assessment. New technology appears at fast pace, which is out of step with the authorities' capacity to ride them into regulation. The challenge for authorities is to keep up with these new developments by giving them a framework and guiding them to maintain a controlled level of acceptable risk. Herewith, we came to the end of this video. Hope you enjoyed it, and thanks for watching.